Okay, good afternoon. My name is Cheng from Southern Illinois University, Carbondale. Today I'm going to present subspace clustering using log-determinant rank approximation. This is joint work with Chong Peng, Kang, Zhao, and Huiqing. Here's the outline of my talk. First, I will give a brief introduction to subspace clustering. Then I will introduce the log-determinant rank approximation. Then I will apply this to subspace clustering. I will discuss a little bit of the optimization of this objective function because it has some of our contribution, I believe. Afterwards, I will show some experimental results. Okay, first introduction. It is well known that high-dimensional data often lie on low-dimensional structures. Recovering those low-dimensional structures can reveal and also preserve the structure of the data set in many problems. It can help address many problems in data mining, for example, dimension reduction, regression, classification, etc. So the goal of this study actually is to find low-dimensional structure, low-dimensional representation of a high-dimensional data set. Traditionally, principal component analysis, the so-called PCA, has been widely used for many, many years to find the low-dimensional structure. However, PCA assumes that all data points are from a single subspace. This may be a problem because in many practical problems, the data points may be from multiple subspaces, and the membership of the data points are unknown. So, for example, if you look at a very simple illustration here, this illustration is due to Dr. Vidal at Johns Hopkins. So the data points are sampled from 3 structures, 1 plane, 2 lines. So it is very hard to approximate all these points using simply one subspace. So there is a need to find all clusters in all subspaces. So subspace clustering is exactly for this purpose, to meet this need. And it is also called a general clustering. It has a number of applications. For example, in image segmentation, face clustering, motion segmentation. In system theory, it can be used for hybrid system identification. Subspace clustering methods have been there for quite some time. As far as I know, from early 1990s, there are some different works on this topic. Also, according to Dr. Vidal, there are 4 groups of methods for subspace clustering. The first group is called algebraic methods, including matrix factorization, generalized PCA, etc. For this group of methods, usually they cannot handle noisy data so well. So in other words, these methods are pretty sensitive to noise. In order to reduce the sensitivity to the noise, iterative methods can be used. This group of methods include k-planes, k-subspaces, median k-flats, etc. The drawback of this group of methods basically is it oftentimes needs to know the number of subspaces beforehand. Sometimes it even need to know the dimension of each subspace. So in this case, it is not so easy to use in some cases. The third group of methods is called statistical methods. For example, it includes mixture, probabilistic, PCA, ALC, agglomerative, lossy compression, and ransack etc. This group of methods also has similar drawbacks to the second group of methods. That is, oftentimes it needs more or less some of the information regarding the number of clusters and also even the dimension of each subspace. The fourth group of methods, is called spectral clustering-based methods. This group of methods provide the state-of-the-art performance. So we basically, focus on spectral clustering-based methods. There is a key challenge for spectral clustering-based methods. That is how to define a good affinity matrix. Oftentimes, in data mining, people make use of distance-based affinity matrix. But in subspace clustering, this is not so good. Oftentimes, it cannot work well. This is because 2 points may be close in distance, but they can belong to 2 different subspaces. And vice versa, 2 points may be remote in distance, but they can belong to the same subspace. So there are different ways to define the affinity matrix. For example, using a matrix factorization method, local subspace affinity, LSA, locally linear manifold clustering, sparse subspace clustering, SSC, and low rank representation, LR. So in our work, we basically take a low rank approach, but we didn't make use of the popular nuclear norm method to minimize the rank. This is because actually nuclear norm is not a good approximation for our problem. Even though nuclear norm is convex, it's easy to optimize. It has been widely used in recent years, but it is basically a summation of all the singular values. So oftentimes it may provide, it may give a big deviation from the true rank if there is a significantly large singular value. So this is why we propose to use a log-determinant approximation for low-rank approximation. So this is this f of x is this determinant rank approximation. Even though in the literature, actually, Faisal in 2002 in her PhD dissertation, she proposed to use a form of log-determinant function, but she proposed to use log-determinant of I plus sigma I. So we think that that sigma actually will basically magnify the noise. So we propose to make use of this form of log-determinant. So why can we expect better performance using this log-determinant function? Basically, we can understand in this way. If, for example, a singular value is very big, 10,000, for example, if we make use of the nuclear norm, it will directly contribute to the nuclear norm 10,000. However, if we make use of this log-determinant approximation, only contribute to the value about 10 or something. So it significantly reduce the deviation for the approximation. So this is intuition why we make use of this form. We apply this approximation to subspace clustering. Here, A is a data matrix. We decompose the data matrix into B plus S plus E. B is a underlying clean data. So it satisfies a property that is B equals to Bx. This is a so-called self-representative property. So it can be understood in this way. That is, any data point, basically is a linear combination of all the other points in the same subspace. So this is a so-called self-representativeness property. And then we make use of S to capture the noise and also the corruption. So in this objective function, we make use of the L norm. L norm can be, for example, 1 norm, 2, 1 norm, etc. E basically represents the fitting error. Okay, that's our objective function for recovering X. After getting X, basically we can get an affinity matrix W by using some post-processing methods. For example, we do the singular value decomposition of X to get U sigma V, and then by using U sigma square root, we can get matrix M. And then for each row of M, we do normalization. Eventually, by considering the correlation of those normalized rows of U, we can form the affinity matrix W. Finally, we can make use of any spectral clustering method. For example, NCART, normalized CART method to do clustering. Okay, so I want to briefly discuss the optimization method for our objective function. First, in order to do optimization, we perform a relaxation. Instead of using the constraint optimization, we perform the relaxation so that we get a unconstrained optimization objective. Afterwards, we do variable, change of variable. We basically define a new variable I minus x to be y, and then we make use of the augmented Lagrangian. So these are basically pretty standard, and also the previous speakers also talk about these methods. I wouldn't cover all the details. For the L objective function, the augmented Lagrangian, basically we do optimization for each variable by fixing all the other variables. So basically, this is a coordinate block coordinate descent method. So we have the optimization stages listed here. For B optimization, basically it is a ridge regression, very easy. We can get a closed form expression. For S optimization, depending on different norms, we can also have a closed form expression. For example, if we make use of the 1 norm, we can get a closed form expression as given here. It is basically the soft thresholding. For 2-1 norm, we also have a closed form expression. For Y, again, it's a ridge regression. We have the closed form expression. For lambda and rho update, it is standard. So the big problem is for X optimization. Here, X is a non-convex objective function. So for this one, actually, we can reduce it to be vector optimization. Originally, it is a non-convex matrix optimization. We basically reduce it to be vector optimization. This vector optimization actually is a so-called Moreau-Uceda optimization in optimization. So it has closed form expression. Okay, actually, to our best knowledge, we think that we didn't see any such kind of results in the literature. So we stated in a theorem for any f of x, as long as it is unitarily invariant. So basically, we can write this capital F of x into F composite sigma of x. Sigma of x basically is a singular value of x. So for this, we can reduce matrix optimization given there minimization of F of x plus half rho x minus d Frobenius squared. So we can reduce it to be a vector optimization given at the bottom row. So this is for any f. It is true. Okay, we also provide some theoretical guarantees for the convergence of our algorithm. Basically, we mathematically proved the existence of the convergent subsequence, and the limit point should be a stationary point. Empirically, we always observe the whole sequence convergence, but currently we haven't been able to mathematically prove it. We are working on this to provide the whole sequence convergence. Eventually, let me show some experimental results. First, face clustering. So we have a bunch of face images. We try to do the clustering so that it can form different groups. Hopefully, each group corresponds to one person. So this is face clustering. Okay, for this, we show our results. The last two rows, scalar 1, scalar 2, 1, basically means subspace clustering using log-determinant approximation are our results. So compared to the other methods, we compared to, for example, SCC, SSC, LRR, etc. Compared to those methods, we obtained a significant improvement, especially in terms of the mean error rate. Another observation is when the number of subjects become bigger, our performance actually degrades gracefully, while for the other methods, the degrades are very severe. Then we show the decomposition. For the noisy image, basically, we have A equals to B plus S plus E. So basically, you can notice that the outlier can be well captured. The outlier basically are in sample or in example outliers. Okay, now we show some results on motion segmentation. Motion segmentation basically for different points, moving points on different moving objects. We try to do segmentation of those points so that each group should correspond to one moving object. So this is sometimes challenging because there may be occlusion. For example, for this working person, sometimes it walk by this tree, and there will be occlusion for the points on the trees. So you may ask why the tree is moving, because the camera is moving. Okay. Okay, so I briefly show some results on motion segmentation. Our results, again, last two rows improves the performance of upon the other methods. Regarding the parameter sensitivity, we can show that for quite a wide range of values, our methods are pretty stable. So we also, studied the sensitivity to the initial values. We also see the stability. Regarding the motion segmentation, the parameter sensitivity. Eventually, we show some the time. So the time complexity. You can notice that in terms of the time, our method actually is pretty fast. Okay. In conclusion, actually, we propose a new approximation to approximate the rank, and we apply it to the subspace clustering. And we built an efficient optimization algorithm to do optimization. For each subproblem, we can obtain closed form expression. And we also, conducted experiments. We observed improvements. For future work, we can, we want to, improve our methods theoretically and computationally. Eventually, I want to, answer some questions if you have, and want to Thank you.
Okay, there is time for a question.
No, just a main comment. There was recently a huge breakthrough in the problem of clustering subspaces by Vada Jan, a provable global 1 plus epsilon approximation for this problem in Soda, I think 2 years ago. And we also, with Christian Zoller and Melanie Schmidt and me, Feldman, we improved it. The problem is no one implemented this, although it's supposed to run in linear time. It's this in n, so it would be nice if someone will try to actually do benchmark with the proper heuristics and this kind of provable approximation. Do you know about this result?
I believe that if the method you mentioned is about 2 years ago, then I think that we basically, probably at least we read the methods.
It's about costs essentially, costs for subspace clustering. This is the name. So we do data reduction and then run exhaustive search on the very small data.
Okay.
I can give you a link some later, but it seems extremely relevant. And
I couldn't immediately recall because we really have a large body of literature. We read many papers. For that one, we also compared with some methods from Dr. Weidel you mentioned.
But they're all heuristics, right? There's no provable approximation to the global optimum. That's the problem with all these techniques.
Yeah, I believe so.
Yeah, and the one that I'm talking about are provable approximation for the global optimum, not the local one. I think this is the great advantage. And unfortunately, the paper is not very readable, so it would be nice if someone will implement them and actually compare.
I read his newest paper, published on pattern recognition letter, basically either this year or last year, maybe early this year. So he indeed provides some, convex formulations. Or even the formulation is not convex. He provides some, probably some guarantees. So I think that in terms of the performance, our method is very competitive. But right now, for our method, indeed, we didn't have the guarantee for the global optimality. So we try to improve upon this. Yeah, thank you for pointing me to this reference.
I think this will be an excellent discussion about whether we can achieve to better than heuristic results in clustering and whether we can have some proofs on that. There is always a lot of space for discussion, but first let's take this speaker before we go.
Thank you.